Okay, we'll look at a few relations between different metric spaces and between their topologies. Okay, so first of all, let's look at a definition. So we have a space X, and if we have a subset, so this time it's a metric space X, and a subset A, we know we can put a metric on it by restricting it. So the first question is, can we do the opposite? That is, or what do we mean by doing the opposite? That is, we have X and we have A sitting here. Can we put it correctly into this? So that is what is called an isometric embedding. So an isometric embedding. So isometric embedding, let's call it F from A to X between metric spaces is a function such that distance between f of x and f of y is distance between x and y for all x, y in A. Let me change the terminology. Let's call these x and y, because even though in our example it was a much smaller space, it need not be. So x, y in x. Okay. So the following thing I'm calling a theorem that's really easy. So if we have an isometric embedding, any isometric embedding well, we know two things about it. It is continuous and injective. I'm not going to try to write out a proof. It's actually really easy. It's continuous because we need epsilon. Given epsilon, we need delta. You can see that delta equals epsilon works. Okay, it's immediate because distances are actually preserved. And it's injective because if the distance between f of x and f of y is f of x is f of y, means that distance is 0, which means this distance is 0, which means x is y. Okay, so I can say proof is an exercise. Okay. Now specifically, suppose this is also onto, then x and y become equal to each other in a strong sense. An isometry f from x to y is surjective. So as isometric embeddings are all automatically injective, but if it's a surjective isometric embedding, and so hence bijective isometric embedding, it's called an isometry. So this preserves the distances. Then you should regard as x and y as being the same metric space. Okay, I mean they're isomorphic in the appropriate sense. More generally, one would like other notions of being the same, and that's what we'll look at next. There is something that sits in between, which I'll mention in passing, but the other important point is, now let's not look at two different spaces. Let's fix a single space. Okay, so now let D1, D2 be metrics on X. And here's the definition. D1 and D2 are equivalent if they give the same topology. So isometric means they actually give the same distances. Equivalent means they merely give the same topology. Of course, if it's a space in itself, then isometry would be just equality. I mean, the natural identity being an isometry would be just the metrics are equal. So if you're looking at two metrics, they're equivalent if they give the same topology. They need not be equal. So example is, for instance, if I look at L1, L2 and L infinity on Rn are all equivalent. And there is a criterion for equivalence. So criterion for equivalence, so I'll say exercise and I'll sketch it. So I'll say this as an exercise as making a precise statement, and then I'll just draw a couple of pictures to clarify what it is. So state and prove. A criterion for equivalence. in terms of open balls. So the open balls are different in different metrics. So what is this criterion for equivalence? Okay, so let's look at, for example, let's take a point. Okay, and if I look at L1 ball, then it's where the sum of mod x plus, so I'm taking R2. L1 norm is mod x plus mod y in R2. So the L1 ball will be the sum where this is less than R2. So the L1 ball will be a diamond. Okay. Now what does it mean to say that the L1 norm and say L infinity norm are equal to each other? Okay. So this is not very symmetric, but that's just my pictures not being great or even good, but the idea should be clear. How about L infinity ball? So L infinity ball is where you're looking at mod of x, y both being less than r. So the maximum of them is less than r, both less than r. So what we want to say is that any L1 ball is open in L infinity topology, which means this is the center of the ball is an interior point, which means if I'm looking at basic neighborhoods, that there is an L infinity ball for a different radius which is contained inside this. And what are L infinity balls? These are just your ordinary squares with sides being parallel to axis. So indeed you'll find an L infinity ball, which I will draw with straight lines, inside this L1 ball containing these. Okay, perhaps I will try to make these parallel to the axis a little bit better, since that's what happens. So L infinity ball looks like this square. So inside this we can find an L infinity ball. Okay, and how about, and note, inside this we can find an L1 ball. Yes. Yeah, that is the correct color. Let's make it a bit thinner. So inside a square I can find a diamond containing the center, or indeed any other point of the diamond, and inside the diamond I can find a square, and so on ad infinitum. Okay, how about the L2? Well, the L2 balls are all circles, so rather discs, their boundaries are circles. So we can find a circle outside here. Perhaps I should be using a different color. Let's make them orange. So given a circular disc, inside that I can find both diamonds and squares. And if one can possibly draw it, if I had my center a little better, if my center was a little better, let's take my center to be just a tiny dot. Okay, so let's look at an orange circle here. And one can try, it'll need a little hand skill, but amazingly I succeeded. Note, you can draw a circle that contains the dot that is contained inside the diamond. So if you are looking at the outer one should also be a nice circle. Let's not unnecessarily make it squiggly. Oh. So given a ball around the black point, which is hardly visible now, in any norm you can find a smaller ball in the other norm centered around this. Okay, so I said norm, but really you're talking metric in general. So these metrics are all equivalent on R2 and in general Rn because of this criterion, because this will tell you that if your open ball in one metric is open in the other and vice versa. Okay, so then because anything is a union of these balls, it's also open in so the set of open sets, the collection, the topologies are equal to each other. Now you might ask, why bother to give them different names and so on if they are equivalent? Well, one thing is the metric properties matter, but that's not one reason, and which is important in some things like geometric group theory. But the other reason is that when we pass to infinite dimensional spaces, they are not equivalent, not at all. They're quite different from each other, and their differences are quite important from each other.